So let's get started. We have another person here who's a candidate for our J.D. Stranathan Assistant Professor in Experimental Particle Physics. And this is Seth Schick. And he got his undergraduate degree from Toronto. And then he was a grad student, got his PhD from MIT. And now he's a postdoc at Caltech, and he's on CMS experiment, and he's gonna talk to us about exploring knowns and unknowns at the energy frontier. So let's welcome Sid.
Okay, so thank you very much for the invitation and the opportunity to tell you about some of this exciting science and explorations that I've been working on for the last several years. And also a little bit about what are the kind of ideas that can push us further beyond the current frontiers. So before I take you on this journey to the high energy frontier, I'm going to start with a very brief kind of motivational interlude. So the high energy physics, my field of study, is kind of the modern incarnation of an ancient discipline, and it's basically focused on answering a really simple question, and that is what are the laws that govern how nature works? So how does it actually behave? And so the modern view on that kind of question is to use an approach which is basically following a reductionist paradigm. And that is to say that we try to understand the behavior of macroscopic phenomena in terms of the dynamics of its microscopic constituents. And so that for us humans, that is actually very intuitive because it is something that we've also probably experienced as kids. So here's a photo of these two girls. They kind of found this interesting yellow rock here. And so they would like to kind of understand more about it. And the way they do that is to take a big hammer, smash it, and actually they use the sock as protection. So it's kind of, there's safety features too. And then once they smash it, they look at the pieces, and they actually discover that this boring rock actually has a lot of structure and symmetry inside, because they actually find that there is some crystals growing inside. And naturally, she's extremely excited about this discovery. So this kind of story is, I think, completely analogous to the kind of things that we do at the high energy physics frontier, because what we do is we have these machines, with unprecedented power. They accelerate particles to extremely high energies, and then we smash them onto each other, and then we look at what's coming out of this debris in order to understand something fundamental about interactions and matter. So from quantum mechanics, there is a very simple relationship between the distance scales delta x that one can probe to the amount of momentum or energy that one has to pump into the system to explore this distance scale. And so in order to understand phenomena of the very, very small, you have to smash particles at very, very high energies. And so to put some numbers on this, the highest energy collider that we have currently running has an energy of 13 TeV, and I've calculated what that distance scale corresponds to is 8 times 10 to the minus 21 meters. And in more human understandable format, this is 100,000 times smaller than the radius of the proton. So that is basically our distance frontier. This is as small a thing that we can currently see. And the way to understand particle colliders is that they are basically the world's most powerful microscopes. Okay, so there's been a long history of success in this this way of doing this science. The first success was achieved in 1932 when Cockcroft and Walton, they succeeded in accelerating alpha particles and smashed them onto lithium nuclei, and actually achieves the first man-made splitting of a nucleus. And then this was followed later in the 60s by scientists at Stanford Accelerator, which actually split the proton by shooting electrons at protons and finding structure. Then in the 70s, 80s, and 90s, there was a progression of successes where we discovered more structure and more particles with the charm quark, the W and Z bosons at CERN, and then in 1995, the top quark. And so from this string of successes, there emerged a pattern of the matter content of the universe and how they interact with each other. And so this was dubbed the standard model of particle physics. It consists, matter in the universe consists of 6 types of quarks, 6 types of leptons. They come in kind of 3 families. And then the interactions between these matter particles are mediated by these bosonic force carriers. So, for example, the electromagnetic force is carried by an exchange of photons. The weak nuclear force is carried by an exchange of W and Z bosons. And then the strong force is carried by exchange of gluons. And then at the center of this whole thing, holding everything together, is the Higgs boson. And in fact, before the start of the LHC, this was, in this picture, the only really missing piece. It was a crucial missing piece, but it was a missing piece of that puzzle. Okay, and so enter the main subject of my talk, which is the Large Hadron Collider. So this is our new frontier. Here is an aerial photograph of where the machine is lying. It's underneath the ground, but this is where it kind of maps out on the ground. And so this is Switzerland. This area here is France. It has a circumference of 27 kilometers around with an energy of 13 tera electron volts. And then it collides protons on each other. And it does that 40 million times every second. And so for you to understand a little bit about how much energy we're pumping into this machine, every time we fill these electrons with beams, that is equivalent to the energy carried by this 10,000 ton aircraft carrier traveling at 20 miles per hour. So we're putting a tremendous amount of energy into this. Just imagine that thing crashing into a wall, and that's the kind of destruction that we can cause. So this experiment is basically big science personified. We are not just another collider experiment. The size and scale are unprecedented. This is a photo of the CMS detector apparatus that I work on. It has a weight of 12.5 kilotons, and it has over 75 million electronic readout channels. So these are numbers which are on the order of like 1 order of magnitude larger than anything that we have built before. Just the raw amount of data that is put out or that is collected by the experiment is something like 1 gigabyte every second. And if I integrate that to 1 year, that it amounts to something like 10 petabytes per year. And to understand how much that is approximately the annual amount of videos being uploaded to YouTube. So we're making the same amount of data as YouTube. Okay, so it's also a collaboration of a global scale. This is a map of all of the institutes that are part of the CMS experiment. And as you can see, we span basically almost all continents. And here's so the CMS collaboration, which I am a member, is made up of 2,700 physicists from 180 institutions and 43 countries. This is our attempt at a collaboration photo taken at CERN, where we also put this life-sized poster of the detector, so you kind of see how large that is. And I was actually able to find myself in this photograph. Okay, so let me spend a couple of minutes going over what makes up this detector and what are its capabilities. So this is a cross-sectional view. So the height is approximately, like, from the bottom to the very top is like 6 stories. So at the center of this detector is an unprecedented 3.8 Tesla superconducting magnet, solenoid. This is used in order to bend charged particles so that we can measure its momenta. Then those charged particles are tracked, and their signals are tracked by the world's largest all-silicon tracker. And then electrons and photons, they are measured by the electromagnetic calorimeter. This is a a device made of 75,000 crystals of this lead tungsten material, this is the picture of one of them. Here's a photo of how they're put together, for example, in the one end of the end cap. And the novelty of this is that it has extremely good energy resolution. So it can measure the energy of high energy photons with a precision of as little as 1%. And that is very important for the Higgs physics that I'll discuss later. Then charged and neutral hadrons that are produced, they're measured by a brass scintillating hadronic calorimeter. Here's a photo of it being installed. This is kind of on the just inside of the magnet. And then these are photographs of the scintillator and wavelength shifting fibers that collect the light that makes the signals, that are the signals of these particles. And then at the very outside of the magnet, we have these gas tracking chambers which are able to measure trajectories of muons, which when they are produced travel right through. And these serve as both tracking detectors and also as identification detectors, because the only thing that makes it out there are muons. Okay, so then at the core of the whole process, the high energy physics, the study of high energy physics is really exploratory. So we are exploring the frontiers of science. And so just like these actual frontier explorers, there are things which we try to go for, try to find at the outset. And so, for example, for Columbus, he was trying to find these trade routes to India and China. And if you are among the very fortunate ones who actually succeed in finding not what we were fighting for, but actually a completely different thing that you didn't even knew existed, as Columbus did when he actually hit on America. In fact, just in high energy physics, just like in this situation, these kinds of surprising discoveries of things that you didn't even knew existed are much more valuable in terms of advancing the scientific knowledge that we have. So there are kind of two tracks in our field. We look for things, and then we try to find things that we didn't even think of. Okay. So what are the things that we tried to find at the LHC? So at the beginning of the LHC, there was a kind of inconsistency in the theory of electroweak interactions that sometimes in certain situations meant that it broke the laws of probability. We didn't understand where mass came from. So these were questions for which the community had the kind of consensus that the Higgs boson would be the thing which would kind of allow us to understand that. Then there were other questions for which there were many possibilities and no real consensus, like what is going on with the universe apparently being fine-tuned, what exactly is dark matter, maybe forces can be unified in some way that we try to understand. So these are the things which drove or motivated the directions in which we tried to search for or explore in this frontier. But at the back of our minds, we were all secretly hoping that we would find something that is none of that and totally different, and that would tell us the way that we would move to the future. Okay, so in the first part of my talk, I'm going to talk about this, which was the main focus at the beginning of the LHC, how to find the Higgs boson. So the Higgs boson at the LHC can be produced in a number of different ways. The main way is for two gluons to collide together and make a Higgs via this loop of top quarks. Then it can also be produced with fusion of W and Z bosons, or in association with them, or together with two top quarks. So then once it's produced, it can decay in all of these different ways. And the two decay channels, which are the main discovery channels, are the decays to 2 photons and 2 Z bosons. And these guys are going to then subsequently decay to each to 2 leptons. So you will have 4 leptons in the final state. Okay, so here's a plot of the production rates for Higgs and various backgrounds, and you see that the rate of production for Higgs is something like more than 3 orders of magnitude smaller than the main backgrounds. And so that makes it extremely difficult to detect even when you've produced thousands of them. And so this problem of finding the Higgs is actually is the prototypical problem of trying to find a specific needle in a needle stack. And so the use of big data techniques is really one front which we pushed a lot when we tried to do this search for the Higgs boson. So because I spent quite a lot of time working on these things, I'm going to take you through one of these examples in order to illustrate the power of these techniques. And so machine learning in high energy physics really came to fruition at the beginning of the LHC. They were developed and used at all levels of the Higgs search. So starting from identifying specific particles to measuring the energy and momentum of them, and then to finally deciding or extracting signal from background using kinematic observables. And so I actually worked on all of these aspects, and I'm going to give you one example which is kind of instructive. So the example is how to identify electrons. So electrons have specific features when they interact with material in the detector. So in particular, when it hits the electromagnetic calorimeter, it will induce a shower. This is what is represented by this blob here. So it turns out that real electrons make a shower like this. And in fact, most of the electrons which are fake, not real electrons, but something else that looks like it, they tend to be things where you have 2 different particles that showered very close to each other. And so what is not surprising that what you find when you look at these width of the shower part, this is a variable which is the width of the shower. You find that for real electrons it's a little bit narrower than for these fakes, and that reflects this kind of situation. Then there are other variables that are useful for discriminating real and fake electrons. So here's an example of the spatial matching between calorimeter and track positions. And you find that for fake electrons, they're a little bit more dispersed. And that's also related to the fact that fake electrons tend to be of this type where they are actually 2 different showers. So then if you take each of these features alone, they constitute kind of what is technically termed weak discriminators, in the sense of they themselves do some job, but they don't do a tremendously good job in terms of getting a pure sample. And especially with this one, you can kind of appreciate that I'm not able to figure out exactly with just that variable what is happening. But what machine learning allows us to do is take all of these variables, there are several others too, put them together, combine the information, and not just combine the information, but also combine correlations between the different variables. And if you pay attention to some training parameters and protect against overtraining, you will end up with a single discriminator that becomes a very powerful discriminator. So here's an example. This is the discriminator which was obtained from training those previous weak discriminators that I talked about earlier. So this is a log scale. So now you see that the fake electrons are way peaked over here, and the real electrons are much peaked over here. So you have one variable which is extremely powerful. And in fact, this variable allowed us to improve background rejection by a factor of as much as 2 to 3 over conventional methods which don't use machine learning. Okay, so in fact this tool, after we developed it for the Higgs search, was in fact became widely used throughout CMS in order to do other things like measurements and searches. So this was a very important tool for the whole community. So here's a slide which just gives you a rough idea of the kind of scale of use of machine learning, I just tried to make a list off the top of my head of all the machine learning tools that I could remember was used in the Higgs search. And so the story is that, or the point is that the real systematic use of these machine learning tools in the context of trying to find the Higgs was really powerful when combined together and really gave us a big boost in terms of being able to find the Higgs as early as we did. And so all of that work translated into this situation in 2012. This is the channel that I have worked on, the Higgs 2-4 lepton channel, and the discovery was made with a combination of the 2-photon channel and the 4-lepton channel. So this was a huge success. Everybody celebrated. Here's a photo of our celebration. Actually, I just missed being outside the photo, unfortunately. I kind of lined up very early, but didn't couldn't make it inside. Okay, so now beyond the Higgs. So once, just like many great scientific discoveries in the past, the Higgs boson actually brought more questions than answers. This is the kind of stuff we like about discoveries. One of the things is that there is this problem of the gauge hierarchy, which is that when you try to look at radiative corrections to the Higgs mass, things like contributions from a top loop, you find that they want to contribute extremely large values. And so that is completely contradictory to what we actually measure. And so there seems to be something weird going on there. In addition, the Higgs seems to be at the edge of an abyss. The stability of the vacuum, or the ground state of the universe, is actually not so stable, I mean, where we are. So it's actually metastable, which means that at some point it will decay, but its lifetime is greater than the lifetime of the universe. So that is another very weird situation to be in. So it's kind of even hard to think about what that means. So all combined together, we seem to find ourselves in a really weird situation where there is extreme and unnatural fine-tuning, and or maybe we just don't understand what's going on with the way to interpret these problems. Okay, so then there are other unsolved problems which I talked about earlier, and the LHC offers a very direct window to understand and explore and address some of these problems, especially in when the LHC was the energy was upgraded from 8 TeV to 13 TeV. This happened in 2015 with improvement of magnet training and so on. This was a time which presented a very unique opportunity to try to go out and explore what is there at the edge of the frontier, at the edge of things we can probe. And so the next part of my story will be an exploration of that. Okay, so what kinds of things can we look for? So there are many competing theoretical proposals. They range from supersymmetry to extra dimensions to some additional strong force. And what is clear is there is no strong consensus on any of these things. There's a lot of overlapping and different proposals, and they kind of have their own advantages and disadvantages. And so the key then for us who are actually doing this exploration is to really exhaustively look and just measure and understand everything that we can see. And then remember secretly that we hope that we're going to find something completely different. Okay, so I'm going to focus on one specific example of these things that one can search for, and that is supersymmetry. So in its most basic form, you can kind of think of supersymmetry as some extended symmetry which predicts that for every particle that we know, there is another partner particle whose the only difference which is that its spin is different by a half, unit of a half. And so this example is actually not really random. It is kind of a very compelling example among the things that can be done. And the reason is that it actually solves a number of problems simultaneously. And so one thing that it solves is this hierarchy problem that I discussed earlier. So because every particle has a partner, the spin is off by a unit of 1/2. These radiative corrections to the Higgs mass, they actually cancel in pairs. So this top loop gets canceled by a stop loop and so on. And so you achieve a kind of natural solution to this fine-tuning problem. It's actually, they all cancel, so there's no fine-tuning. Then supersymmetry also unifies gauge couplings. Here's a plot which shows that with supersymmetry at 10 to the 16 GeV, the strengths of the electromagnetic, weak, and strong forces, they come together. Whereas if you don't, then they actually don't come together. So this is a very interesting and suggestive feature that seems to be happening. And then on top of that, supersymmetry also provides a very specific particle candidate for dark matter. And that is the lightest supersymmetric particle will be stable, and therefore it can be the dark matter. So I've told you all the good things about it, but in practice, this thing is extremely difficult to search for because there are so many particles that can be produced. And then there are so many unconstrained parameters that we don't really know about these particles. For example, their masses or the way they decay. And so that makes this search scope extremely huge. It's basically can do a lot of different things. And so it's not clear how you would exactly search for it. And so the challenge of in terms of analyzing the data is to try to cover as much space as possible in order to be sure that you've kind of covered all the possibilities. However, for exactly the same reason, these supersymmetry searches are extremely sensitive to other things which are not supersymmetry, and they're also sensitive to these surprises because we cast an extremely wide net. So we look in all kinds of places, and when you do that, you are more likely to find surprises, given that you don't know what these surprises should be. Okay, so let me go through this analysis that we have done. So I've told you that the search scope must be extremely broad, and that means that we have to search inclusively, so looking at all kinds of signatures. But in order to enhance sensitivity for each specific signature, you need to categorize so that each specific signature kind of gets its own box so that it is enhanced by its and not contaminated by other signals. And so here I've drawn a kind of cartoon in this plane of counting the number of leptons, counting the number of jets, counting the number of B jets. And so to give you an example, a search which is more focused might look for something like these bottom squarks being produced. They decay to 2 B quarks and dark matter. So you might look in this region with no leptons, 2 jets, and 2 B tags. Then you can look for something like this, where you have 2 gluinos produced, and each of them decay to 2 of these light flavored quarks and dark matter. And then you would look for it in a region which is no leptons, 4 jets, and no B jets. So instead, our approach is to kind of cast a wide net and cover all such signatures with their own categories. So basically cover all of these possibilities. Obviously, this is much more challenging because one, the increased scope is just bigger, more data to handle, and also the fact that when you do this, you have to model the backgrounds very accurately in all of these different places, and because they kind of behave differently, that is much more challenging. Okay, so a few words about what tools to use for making these discoveries. So historically, we have used mass resonances. In fact, this is something I explained earlier at lunch in terms of this masses on a spring. But so these are kind of similar. So these things we've discovered in the past, including the Higgs, were found with a mass variable, and then you typically see something, just a bump or a peak coming out of a flat or falling background. So this is a very distinguishing feature. Unfortunately, when you have decays to dark matter, and in particular if you have decays to 2 of them in the final state, then you can no longer fully reconstruct that resonance, and so you don't have enough information to actually make that peak. So instead, what you will make is something like that. In one of these typical search variables, you're going to see a signal that just creeps up at the end of the spectrum with an enhancement at the very end. And so that is very hard to search for, because you need to know very accurately exactly how this background shape behaves, because like if the slope is a little bit different, you have just washed out your signal. But on the other hand, if we make some appropriate choice of boost and choice of reference frames, then we can actually approximately reconstruct the decay. So you can kind of recover this bump, although this bump is much broader than what is typically what I showed in the previous historical examples. And that is what is done with these so-called Razer variables, what I call MR. So it converts something like this into something like that. So that is shown kind of in a card from the simulation here. This is some particular signal, and you can see that it makes a kind of bump, which is relatively broad, but it's still a bump here. Then we have another variable, which is called R squared, is orthogonal, and this thing is sensitive to dark matter and suppresses backgrounds. So for the people who know about these things, this is basically analogous to the missing transverse energy. So it sees neutrinos as well. And one of the additional good features about these 2 variables is that when we look at the backgrounds, they actually have a very distinct pattern of fall off. So they kind of fall off exponentially in both directions. And that is a feature which I'll use later. And so this construction works for any pair-produced particles decaying to a part which is visible and invisible. And so it is kind of general in the sense it doesn't require you to have specifically these objects or these objects. As long as you have invisible and visible, this will work. Okay, so let me get back to background, modeling the background. So I said that this is the most important thing and the most challenging thing. So the dominant backgrounds are production of top quarks and production of W and Z bosons together with jets. And one of the main challenges is actually to accurately model the recoil of a jet. So let's say at leading order, I have this thing where I produce a Z boson and then recoiling against some quark or gluon. However, if you look at more seriously, the situation is actually more like this, where that quark or gluon, it can radiate some more gluons. That gluon can split into other quarks, and then all of those things will then have to hadronize. They make charged particles and photons, and then you have to cluster them, and they all kind of point in a spray, which we call jets. And so it can be one or many, and they can have large angles between them. So this is a very complicated process to calculate, and it's extremely hard to calculate accurately. And so the approach that we take is to take these calculations and the simulation model and then calibrate them to control region data where we can isolate specific background processes. So for example, if I select events with 1 lepton and greater than or equal to 1 B-jet, this isolates for me the top quark background, and then I can look at the data and compared with my simulation. This is these colored histograms. And in fact, what I see is that the fall off in this MR variable in data appears to be a little bit steeper than what that simulation is predicting. And so I convert that into some correction factors for corrections for the simulation. And it's actually done in both MR direction and the other R² variable. And that can be done for all the other backgrounds. So here's the example for W plus jets. If I just require there be no B jets, I get a sample which is mostly W. And in fact, you see kind of the similar trend. So there seems to be a pattern emerging that these simulations require a similar kind of correction. And so we're applying all of these calibration factors to the simulation to get the final accurate background model. So then there's a whole bunch of other things which I don't really have time to go through all of them. For example, we have to validate the identification of B jets. We have to validate the accuracy of modeling electrons, muons, and taus. Then we do more cross-checks to make sure that we know really what our calibration is really working. So we look at top quarks decaying to 2 leptons and Z decaying to 2 leptons. And then there's more, which I'm not going to show. So after all of that, we put all of these things together and we achieve the best kind of model for our background. Okay, so that's one thing. Then the second thing is that, remember that I told you these variables decay in an exponential way. And so that's kind of shown here. We have plotted these two variables, and these histograms are what the Monte Carlo simulation predicts is the shape. And then this dots is a fit. Oh, sorry, the dots is the simulation, and then these lines are a fit to an exponentially falling function. And so you see that that function fits it extremely well in both dimensions. And so what we can, that implies that what we can do is take some take some data which we know does not have any signal and is all background, and then we can fit that to this function and then let the function kind of extrapolate out to the rest of the signal region, and that will be an alternative model for the background. So that's done here. So I've split this 2D plane of these two variables into this kind of rectangular shape. And so I take sidebands. These are regions in which MR and R² are both low. Those are the regions where you have dominantly background and not really any signal. And then I fit those data points to that function, and then I let the function extrapolate out to this region here. So that's what's done, shown here. So these green spots, which are here, there, those are the sideband bins and the data which are used to do the fit. And then these blue bins are the ones that are out here and are just completely being extrapolated. And you find that there is actually excellent agreement between that fitted model and the actual data. So it seems to be working extremely well. So that model provides you a completely different model of the background. That fit provides completely different model of the background. And so we have these two different background models, one based on calibrated simulation, one based on this fit function. And so we can compare them. That's what's done here. So one of these colors is the one method, and then the dots are the other method. And so you see that, in fact, they agree extremely well. And so what this is giving us tremendous confidence that we have got that model right, because we're taking two completely different ways of getting the background model. They have totally different assumptions and ways in which they could be wrong, and we look at them and they actually agree. So this is telling us that we're probably doing something right. And so this is in fact the only SUSY search at the LHC, as far as I know, which does two different models and compares them. And the fact that we have this agreement is a really important verification of assumptions which are made typically in conventional searches where usually only one of these methods is used. So this is telling us that these assumptions that are typically made are probably good. Okay, so now I have this background model. I push into the unexplored region, and we look at the data. These are a couple of examples of these boxes or categories that I showed you earlier. This is like 4 jets with 2 B tags. This is 1 electron with 4 jets and 1 B jet. And so as we extrapolate out here, we see that there is pretty good agreement between our model and the data. So unfortunately, we don't have any surprises. There's also no sign of supersymmetry. However, one of the things that I think we're gaining is we're gaining tremendous understanding or precision understanding of how these standard model background processes behaving way out in the tails of these distributions. So we're looking far out, and they kind of, and we're having a model for them, and it seems like we are accurately predicting them.
There's a question. Do the points that deviate the most also have the biggest error bars?
So yes, and that is, it will always be like that, because if you have statistical, so they are on top of this. So when you have statistical fluctuations, they typically happen in regions where they where the prediction is low number of events, like 1 or 2 events, and those are exactly the regions in which we have the largest uncertainties, because it's so far out, and we have to kind of project far out.
I'm not sure that that's the explanation for the data I'm looking at. Some of those points seem to be pretty well populated, and they have great big error bars because they're far away from the mean. How about for one of the furthest right?
Which one?
That's a low. That's a low. The one in the.
So okay, for example, this has like 1 event. This one is like 3 or 4 events, and it's like a little bit closer to 1.
That's all 0.
Oh yeah, these ones are all 0, so there's nothing there.
Anyway.
So, but it's good. We need. It's good to kind of dig into this and understand, look at it carefully.
But those are events per bin, is that right? Or are they just total events of that kind?
Here it's total events.
Wow.
And this is the ratio between the prediction and the event.
Okay.
So here we're kind of looking at things where we don't even predict any background, and we don't see any background. But we will eventually when we collect more data. So it's a place to kind of look later. Okay. Fine. So then we found we haven't found anything. We have achieved this understanding, but if one is interested in supersymmetry for itself, for example, which some people are, and so we are kind of interested in providing some information on, or some way in which we say how much information did we gain about supersymmetry itself. And so these are what are usually provided in terms of these limits on production of various supersymmetric particles. And so the logic is as follows. So if these things existed at some specific mass or point, then the predicted production rate would be such that we should have seen them. And because we didn't see them, therefore they couldn't have existed. And so that's the kind of thing we're showing in these plots, these limit plots. So typically these things are expressed in terms of specific decay modes. So for example, you can look for gluinos that decay to 2 B jets and dark matter. And so they're plotted in terms of the gluino mass, which is this guy, and the dark matter mass, which is the invisible one. And so this region below that curve is excluded, meaning that if these gluino and dark matter had masses that were these values here, they should have been produced and we should have seen them, but we didn't, so they don't exist there. And this region above it is still allowed, and that means that either it didn't have any production rate, so we even wouldn't have seen them, or the background is so high that we couldn't pick it out if they were there. Okay, so the inclusive approach that I discussed is in fact, because we include all of these different categories, they are in fact sensitive to not just one decay, but all of the possible decays of gluinos. So these are the decay possibilities. And so the limit plot that we are able to show is actually making a stronger statement, which is that the gluino, in fact, does not exist in this region, no matter what the decay is. So for all decays, they don't exist here, and this part is still allowed. Okay, so we've explored as much as we can here at the moment. And so just to give you an idea of how much information we've gained in terms of using supersymmetry as an example, here's the little blip that was covered in terms of a SUSY search in 2009. Then we went to something like that in 2012. And then in 2016, it became something like this. And so we gained a lot of coverage. However, there's all of this other coverage which is not being covered. And so we're not done, basically. And so a lot more remains to be explored. Among things are precision measurements of Higgs production rates. So these cross-sections are known to only the 20 to 30%. We'd like to get it down to 5%. This is something that we can realistically get with the upgrade of the future LHC. Then there are some Higgs property measurements of spin, charge parity, and anomalous couplings. This is something that I worked on after the Higgs discovery, but with the result which is relatively statistics limited, because we had only 20 Higgs events essentially. And so in the future, as we collect more, we're going to gain much more information from doing these measurements. And especially this one is particularly interesting because by measuring these anomalous couplings, if there's any deviation away from these axes that the data prefers, this is telling us that there is potentially a large CP violation in the Higgs sector, and that is potentially going to be a big clue for answering the question of why there is so much matter in the universe compared to antimatter. Okay, then on searches, we have a lot of things to do. There are so despite the fact that we cover this region here, there are some holes in here which are extremely difficult to cover for the reason that the signal starts looking a lot like background, and so there's not so much handles to kind of identify the signals. And so these are going to need a lot more data to kind of get the information out. And then we're not covering all of this other space, which is still remains to be covered. Then there's a lot of deep exploration that we still not done. Namely, so if I look at various measures, this is actually a dark matter search, but you can kind of think of it as a measurement of the missing ET distribution. So this is momentum of recoiling invisible particles. And so out here at the end of the spectrum where we have no events, we have no information at the moment, but as we gain more data, these are going to fill up, and we're going to be able to probe these things. And this is the same, but this is a mass variable. So if we're looking for mass resonances at extremely high values of extremely high values, there are things which can be living there which we're not probing right now. Okay, so all of these things, future goals, require unprecedented luminosity and huge data sets. And so the way I'm thinking about it is in terms of 2 stages. The first stage is to push forward this project of the high luminosity LHC. This is a project where the LHC gets upgraded and have its intensity increased by something like factor of 5 to 10. And then the second stage is to think about pushing forward that energy frontier. How do we increase the energy that the collision energy that we can achieve, and maybe we have some possibility at next generation of colliders. Okay, so this is a kind of a schedule of the high luminosity LHC. So it's at the moment we're somewhere here. We have like including run 1, something like 60 inverse femtobarns. At the end, we're going to get, at the end of the normal LHC run, it will be 300. And the goal for the high luminosity LHC is to get to 3,000. That's a factor of 10 increase. And so an upgrade of the accelerator is needed, including, and this is going to achieve a 5 to 10 times increase in instantaneous luminosity. But unfortunately, along with that result, is that we're going to have something called pileup becoming kind of restrictively large. So these are things which are simultaneous collisions of protons in the same time window. So we collide protons every 25 nanoseconds. And so it's bunches of protons, and you can either have one collision between two pairs of protons or many. And so right now, at the current LHC running conditions, we're seeing pileup on the order of something like 30 or 40 simultaneous collisions. And when we do this upgrade to the LHC, it will come up like something like a factor of 5 to all the way to 200. And so these are event displays, which are trying to convince you that this is an extremely difficult environment to understand these collisions, because you get all of these different collisions. Each of this yellow dot is a vertex, so it's a potential collision point. All of these green things are tracks. These things are calorimeter hits. And so you have a huge amount of signals being produced, and you have to figure out which ones are extraneous and which ones are actually important. Here's information about the future. So this pileup issue is not a niche issue. It is an issue which is here to stay. So when you're thinking about future colliders, like there's some planning of colliders in China or at CERN, which is going to have upgraded energy, bigger, even bigger radius. These future colliders are going to demand even larger instantaneous luminosity, so you're going to face even more pileup. So this pileup issue is a problem which we need to solve for the future. It is not just for the high luminosity LHC, but in general. So what are the kind of challenges that is faced by pileup? So as I said earlier, you have all these extraneous particles being produced. You need to know which ones are important, which ones are not. And so they can be misidentified. I might think that this one was important, but it was actually not. And not just individual particles, but these spray of particles, which we have jets, they can also be misidentified. And so you have a lot of these objects which might be which you might think is part of your event, but should actually not be. And so that's going to confuse you about how to interpret these events. So even the tracking and vertexing is going to start to suffer. So we start having so many collisions happening along the beamline that you're going to have situations like this, where two collisions just randomly happen to overlap in space. And so then the tracker cannot really figure out, because it's so close in space, it can't figure out that it's actually different things. And then you start to have some amount of merging of these vertices. And so here's a plot which is telling you that at the conditions that we expect for the high luminosity LHC, which is this value here, the fraction of tracks that are associated with what I think is the primary is the main collision, is actually 40% of them were not. So we're taking in 40% of these tracks, which basically wrongly. And so that's going to confuse me when I try to understand things about that event. Okay, so then in the rest of the talk, I'm going to try to convince you that one of the major handles for kind of addressing that problem of pileup is to use precise timestamps or time measurements of these particles. So it's kind of an obvious solution. You measure the timestamp of a particle when it was produced. That allows you to identify which vertex it came from. So, for example, if I have a detector over here on the left, and then I have these possible collision points, then if that particle was produced here, it will have needed to travel a longer distance to get over here than if it was produced here. And then on the other opposite end, it will be the opposite. It will be shorter, this one and that one. And then by comparing the timestamps, I can know whether that signal that I saw over here is actually coming from this place or that place. So what is the kind of time precision that I need to do this? It follows a pretty simple logic. So here's a picture or cartoon of what a typical collider beam spot looks like. This is the z-axis, or the longitudinal axis. This is the time axis. And so the width of this thing in the longitudinal axis is typically something like 10 centimeters. And so 10 centimeters gets me the 200 pileup. If I want to reduce the effective amount of pileup by a factor of 10, let's say, so that I get to 20, and 20 is something that we have faced in the past before, so we kind of know that that is something we can deal with. Then I need something like 1 centimeter precision in this direction. And so then I know that particles, most of the particles that we deal with, they always travel at the speed of light. And so light travels something like 33 picoseconds in 1 centimeter. And so what I need in terms of precision at this end is something like 30 picoseconds. So that 30 picoseconds is going to get me a factor of 10 reduction in the effective amount of pileup. And for the kind of parameters that we're thinking of for the HL LHC, a factor of 10 is kind of the right amount of reduction. Okay, so there's been a whole lot of recent work on this topic, and a lot of that work is kind of funneling through the collaborations now, and so it's enabling realistic proposals for having detectors which do this. So, for example, in CMS, we have these proposals to have charged particle timing, so timestamps for particles which basically pions and other particles with charge, to insert an extra detector layer somewhere between the end of the tracker and the calorimeter. So there's a proposal which uses LYSO crystals and silicon PMs. Then there's also timing for calorimeters. And so here, the CMS collaboration has decided to upgrade the end cap calorimeter with a highly granular silicon based calorimeter. And so if one, so there's been a lot of work done on trying to demonstrate that such a type of detector can actually achieve the kind of time precision that we'd like, basically 30 picoseconds. And so I'm just going to go through one recent thing that we've done on exactly that topic. So basically, how sure are we that silicon sensors can actually achieve that calorimeter timing that we need? Okay, so the idea is to measure time resolution for electromagnetic showers sampled by one of these silicon sensors from that high granularity calorimeter prototype. And so we got a couple of these sensors. This is a drawing of what that sensor looks like. It's kind of hexagonal in shape with each silicon pad being also hexagonal in shape and roughly 1 centimeter across. The sensor is 300 microns, and so we designed one of these special readout boards and equipped them with relatively fast amplifiers in order to try to factorize the problem so that we see at the end that the measurement that we make is actually telling us something about the capabilities of the silicon sensor and not some other thing in the readout chain. So we instrumented 25 cells in this board, so, and they have kind of fast amplifiers on here, and then there's a second stage amplifier, and these things are read out like this. And so here's a schematic of the beam experiment that we did. So we shoot electron beams coming this way. There's a little trigger which makes sure that the beam is very narrow. And then we induce a shower with some tungsten absorber. Then that silicon layer is placed just behind it, very close. And then we have, at the very end, a reference timer. So it's basically this device. It's called the Photech, and it's a micro channel plate PMT. We've measured that resolution of this thing to be less than 7 picoseconds. So it is used as a reference timer in order to benchmark the performance of that silicon layer. So here are some photos of the beam setup that we had. So this is us trying to build, put the equipment in the beam line, and also the safety review, which is very important. So here we are trying to take data and look at some initial plots. So one of the things which is I find very nice and interesting is that these kinds of R&D programs are extremely good for training undergrads. So these are 2 of my summer undergrads, and they I think had a really interesting educational experience, because we kind of started them off in the lab trying to test all of these sensors that we were going to use, and then they took the equipment, they moved it to the beam line, kind of built it, and then wired it all up, and then we took the data, and then they did the analysis. So it's a very nice self-contained project for these guys, and they're still working with us, so they kind of, I guess they liked what they were doing. Okay, so here are some results. So this is a plot of the pulse from one of the silicon sensors. So it has a rise time of 1.5 nanoseconds, so it's relatively fast. And then this is the final measurement. So here we measure the time difference between the reference and the time stamp measured by that silicon layer. And so we got a time resolution of 16 picoseconds for this thing at 32 GeV. For 32 GeV electrons. And so that is extremely encouraging. It's telling us that silicon sensors can, in the context of these kinds of showers, they can do the level of precision that we need. And so then the next step is, so having answered that question, the next step would be to put it all together, figure out what kind of readout needs to be done in order to actually achieve it in a large scale. Okay, so then here's a collage of a different topic, which is when, so I said that there's this other proposal in CMS to do barrel timing for charged particles. So this is just to show that we've done a lot of R&D work on these crystal timing aspects, and so I don't have time to go over all of them, but basically it's to say that these work that we've done forms the basis for kind of the CMS proposal being pushed forward. Okay, so I'm going to end in just a few minutes so with the following challenge, which is to say the following. So I told you that the current realistic proposals is to have these extra detector layers, which is going to measure time for us for charged particles. So then the challenge would be, instead of doing that, can we just simply equip the silicon tracker with the capability of measuring timestamps at 10 picoseconds. So then the tracker here, which is represented here by these yellow things, would just serve the purpose of these layers, and we wouldn't need the layers. And on top of that, we have many silicon layers, so we get lots of redundant measurements, and they're going to significantly enhance other capabilities as well, like searching for long-lived particles or things like that. So can we do that? And so there are kind of two challenges, two aspects to achieve that. One is to have faster signals. That means that the rise time is faster. So I want to collect the total signals faster, have it drift less, so that its dispersion is smaller, because like geometric dispersion is really the thing which causes time resolution to become worse. And one of the things that I've been thinking about is this proposal to have 3D silicon sensors. So these are sensors which, instead of getting the signals out from the top and bottom planes, you kind of put this electrode that is like a column that goes all the way down into the bulk of the material. And so when you produce signals, they actually drift only the amount transverse to that column. So the collection is much faster, there's less drift, and there's less dispersion. And as another thing is that that also happens to improve radiation hardness. So that is a technology which I find very interesting to think about and to work with. And then the second challenge is to reduce the noise, or alternatively, we increase the signal size. It's kind of the same thing. And so on the noise, there's a lot of work that one has to do on sensors and electronics. But then for sensors, for increasing the signal, there are these relatively new sensors which try to, silicon sensors, which try to have gain on the signal. So instead of just these ionization signals coming out, you have this layer which is has a large electric field, and that induces an avalanche and makes the signal have gain. So these are called these low-gain avalanche diodes. So that is an object of active R&D study in both CMS and ATLAS as potential options for these timing layers. And so here I took a photograph of this probe station test of this sensor that we had done this over Christmas, just to understand some things about these sensors. And so, okay, so my basically the upgrade work that we're doing now for CMS and ATLAS is paving the way for these promising technologies to really try to make it a reality for the next generation. And so, so the answer is yes, if we work very hard. Okay, so this is my summary. So hopefully I convince you that the high energy frontier is new and exciting, and there's a lot of potentially unknown science that's still to be extracted from it or revealed. And we've really only studied the tip of the iceberg. There's much more deeper explorations, more precise measurements to be done to really get everything, all of the information out. And so the future is both very challenging in terms of all of these things that we have to accomplish, but it's also very bright because there are all these different options that people are putting out, and they seem to be very promising. Okay, thank you. Okay. Oh, there is one question there.
How much significance can you gain if you use radar variables compared to amplitude-based supersymmetry?
Oh, how much significance? So that depends a little bit on what the signal that you're looking for is. So it's particularly good for things that have, like for example, if we have things where the signal is kind of concentrated in one category, it tends to do very well. If it's kind of spread out, then you kind of lose. I mean, then many of the other variables also do the same. So it depends a little bit. Yeah.
Use still plan to be searching for supersymmetry at LHC in 2026?
2036. So I would say that I would not call it the search for supersymmetry if I do it. So as I told you when we talked, I view these supersymmetry searches not only as supersymmetry searches. They're kind of both just exploring out as far as we can and also making very precise measurements of the backgrounds and kind of getting a precise understanding of what these backgrounds are doing way out in these things that we haven't really explored very fully. And so in 2036, I think in terms of the view of doing these measurements out there, there's still going to be things to do out there, but I probably would not call it a SUSY search. Unless we find it, then we might search for other variations.
Well, we're never going to kill Susie, but anyway.
He's not, yeah.
But maybe
Well,
we'll start.
It's going to get slowly killed, probably, in the minds of very few people.
But anyway. Okay, let's thank our speaker.
Thank you.